While the engine is operating at sea level, the throttle valve of a supercharged engine must be partially closed, so as to restrict manifold pressure and prevent excessive cylinder pressure. Imagine the aircraft climbing with rated power set. To obtain rated power, we must set both rated RPM and rated boost. At the start of the climb, the throttle valve would be only partially opened, but as the aircraft climbs, the throttle valve must be progressively opened, either manually or automatically, to maintain the required boost or manifold pressure. Eventually, a height is reached where the throttle valve is fully open, and this is known as full throttle height. Above this height, power will fall off in a similar manner to the way it does with the normally aspirated engine. The full throttle height at rated power settings, that is rated RPM and rated boost, is known as rated altitude. Since the output of the supercharger depends on the speed of rotation of the impeller, each power setting will have a different full throttle height, according to the engine RPM and boost or manifold pressure used. For instance, if the aircraft is climbed with rated RPM, but less than rated boost, then full throttle height at this power setting will occur at a greater altitude than when climbing at rated power, as is illustrated here. If, on the other hand, the aircraft climbs with rated boost set, but with less than rated RPM, full throttle height will occur at a lower altitude than when climbing at rated power, as shown here. In summary, then, the effect of reducing engine RPM, and hence supercharger rotational speed, while maintaining the selected boost pressure, would be to reduce the full throttle height. The reduction in full throttle height happens because the reduced engine, and thus compressor speed, reduces the compressor output. In turn, this makes it necessary to open the throttle valve by a greater amount sooner than would otherwise be the case, in order to achieve the same manifold pressure. The supercharger is designed to maintain a selected manifold pressure. To do this at altitude, the impeller must be driven at a high speed, because of the considerable reduction in atmospheric pressure with increased height. Therefore, at low altitudes, where the air is much more dense, the supercharger produces too much pressure. Consequently, to avoid severe detonation and mechanical stresses due to excessively high combustion pressure, the delivery pressure must be restricted by only partially opening the throttle valve. As the aircraft climbs, the throttle valve must be progressively opened further to maintain the selected boost pressure. To relieve the pilot of the responsibility of constantly varying the position of the throttle lever during the climb or descent, the boost pressure is kept constant automatically by the automatic boost control unit, a diagram of which is shown here. The automatic boost control unit is situated between the throttle lever in the cockpit and the throttle valve on the carburetor. The automatic boost control unit contains an aneroid capsule, which is sensitive to changes of inlet manifold pressure. The position of the carburetor throttle valve can be set by moving the pilot's throttle lever. A landed valve connected to the underside of the aneroid capsule is also positioned by movement of the pilot's throttle lever. Engine oil pressure is directed by the landed valve to either side of a servo piston, which adjusts the position of the carburetor throttle valve in response to changes in manifold pressure. If the manifold pressure exceeds the figure selected by the pilot, as it may do in a descent, then the aneroid capsule contracts, lifting the landed valve to allow pressure oil to be fed to the top of the servo piston, which in turn closes off the throttle valve a sufficient amount to bring the manifold pressure back to the selected figure. If, on the other hand, the manifold pressure drops below the selected figure, as it would in an extended climb, then the aneroid capsule expands, lowering the landed valve to allow oil pressure to be fed underneath the servo piston. This opens the throttle valve to allow more air from the supercharger into the manifold, thus raising the pressure back to that which was selected. We've already seen how the power of both a normally aspirated and a turbocharged engine decreases with increase of altitude. The effect of altitude change on a supercharged engine is totally different. This diagram shows how the power output of an internally supercharged engine increases with increase of altitude, up to full throttle height. This happens because of the different effect that exhaust back pressure has on each type of supercharger. Whereas with an internally supercharged engine, the exhaust back pressure reduces as the aircraft climbs, and thus absorbs less power in the exhaust stroke, because the wastegate of a turbocharger restricts the escape of the exhaust more and more as the aircraft climbs, in order to drive the turbine faster, its exhaust back pressure increases with altitude. As part of the type certificate information, the manufacturer states the engine limitations for each particular aircraft, which include the maximum static or reference RPM. This gives a baseline figure against which the engine's future condition may be checked. A note of the reference RPM is made and placarded somewhere convenient in the cockpit, for example on the relevant RPM gauge. Supercharged engines will normally run at a constant speed at high power settings, under the influence of the variable pitch propeller, and small changes in power will not affect the engine speed. As a consequence, it's impossible to check the power output from only the evidence of the RPM. The procedure for checking that an engine's power output is correct is as follows. Initially, the engine must be run until normal temperatures and pressures are obtained. It must then be opened up to maximum takeoff manifold pressure, or boost pressure. The power must then be decreased until a fall in engine RPM occurs. The reduction of RPM is indicative of the propeller blades being on their fine pitch stops. The engine must then be throttled back further to obtain the manifold pressure quoted by the manufacturer, which in our instance we'll say is 35 inches of mercury. Once the prescribed manifold pressure has been obtained, the engine speed should be within 50 RPM of the engine reference RPM. Once the reference RPM has been established, it remains fairly constant. Any deviation from it would probably indicate some form of engine malfunction. A new reference RPM will have to be established every time a major engine component, such as a magneto, is changed. Before an engine is started, its boost pressure gauge, or manifold absolute pressure gauge, depending on whether the system is British or American, supercharged or turbocharged, will show approximately ambient atmospheric pressure. At exactly sea level pressure on an ISA day, this will mean that a reading of 29.92 inches of mercury on a manifold absolute pressure gauge, or zero boost on a boost pressure gauge, will be indicated. Because the gauge is effectively reading atmospheric pressure from the manifold of an engine that is stopped, with an increase of airfield altitude, the gauge reading will of course fall. And conversely, if the airfield ambient pressure is above ISA sea level pressure, then the gauge reading will rise to that level. The gauge reading at this point, that is, before engine start, is known as static boost, and a note should be taken of it in order that a check of engine power output can be made. As the engine is started, the pressure in the inlet manifold will decrease to read below the static boost figure. It will probably not begin to rise as the throttle is opened until about 1600 or 1700 RPM is established. With maximum RPM selected, that is, the propeller on the fine pitch stop, as the throttle is progressively opened, the inlet manifold pressure should regain the static boost figure at the reference RPM, plus or minus a small tolerance of, say, 50 RPM. The reference RPM will vary with different models of engine, but would on average be 2500 RPM. Any result which is outside tolerance may be the result of a cylinder down on power, the ignition system malfunctioning, a carburetor maladjustment, or even an improperly set propeller low-pitch stop. When making comparisons between turbochargers and internal superchargers, it's inevitable that the question of which is best is asked. If it was just a matter of added performance at ground level for a given cost, then the turbocharger would probably win. There are other considerations to be taken into account, however. First of all, do we only want the added performance at ground level? Unavoidably, in the case of an aircraft, the answer must be no, in which case the internal supercharger, with its ability to increase engine power with aircraft altitude, must be the favourite choice. Secondly, do we require that the response to throttle opening be instant? If the answer to this is yes, then once again the internal supercharger wins hands down. The aircraft engine turbocharger, for all that it is the cheaper option, cannot, with present-day technology, respond to rapid throttle opening without suffering from the phenomenon known as turbo lag. Turbo lag results partly from the inertia of the turbocharger and partly from the time taken by the absolute pressure controller to respond to low compressor output signals. It also takes time for the wastegate actuator to react and close the wastegate. Thus, there is an inevitable delay between asking for power and getting it. Here is a table which illustrates the differences between the supercharger and the turbocharger. This concludes the lesson on power augmentation.